this H is given as Ni upon D. Or in some books or in some notes, you may find written like this, NiAZ, a small ni, but see the very, very slight difference. A small NiAZ. So a small Ni is that turn density.
Density.
Number of turns per unit length.
Length.
So many books, or you may say almost all books, are writing like this, Ni. If you are writing Ni, then it is a small n. If you are writing in terms of capital N, then it is N capital N I by D.
D.
D or L.
Yes, sir.
If L is the length, then L. D is the length, then D. Yes?
Yes, sir. Yes, sir.
Any doubt?
No.
No. So remember this while solving the problem, we may see this one. Then, okay, then same expression, it has been derived using the Ampere's law. So that is the same expression. Finally, the result will come same. That is Ni by D. Okay.
D.
Then another application is the toroid. What is a toroid?
I don't know, sir.
Don't know. No issue. You see, seeing in the figure, you see in the figure, and then can you imagine what is it like this? This is a toroid. So what is actually means it is there?
Coil wounded on it.
Yes. See, here it is a, as you can read it out here also. This is a doughnut shaped. Such shapes are called as this, like this, means one is the inner and another is the outer layer. So doughnut shape set of the windings around a core material. So see, the cross section could be the circular or of the any other shape. So what is actually here is that if you see very carefully, there is an inner core, and from this core to the outer core, the wires are wounded like this, and current I is flowing over this wounding. So there is a difference between the solenoid and toroid. In solenoid, there was no two shapes, means there was only one circular nature, but here there are the two doughnut shape or the two elliptical or maybe the circular shape. As you can see here, this would give you a better picture. As you can see here, there's an inner core and there's an outer like conductor, and the winding is something like this from inner, as you can see here, the cursor from inner to the outer. Yes?
Yes.
And now interestingly, one interesting concept here you may encounter, you see, can you try to explain? That would help you to explore your concept study till now. Here, this, if you can remember, I had already told you that this circle with a dot, what does it represent?
Outward.
Exactly. And the circle with the cross, inward.
Inward.
Yes?
Yes.
If current is throughout the same, why for the inner conductor it is showing like this and for outer conductor it is showing like this? Can you try to answer? At least can you try to apply the question is clear to you what I'm trying to ask?
Yes, sir. Yes.
Yes. So my question is that why it is like this, that for the inner conductor it is the means you may say the clockwise, and for the outer conductor it is anti-clockwise, or that is outward or inward, same. This is also explained in terms of the clockwise and anti-clockwise. So why it is like that?
Means here in outer
See, if you see here, if suppose the current is flowing something like this, then you try to see if it is something like this for the inner conductor, if it is the direction of the current is clockwise, for outer conductor it would be the anti-clockwise.
Okay.
Because see, the same current is flowing. So if it is something like this here, then here it is anti-clockwise. Then here for outer one, this should be something like this. Then only it can flow like this, na? So here it is, see, here it is like this, but here it is like this. So here it is clockwise, but here it is anti-clockwise. Or maybe the vice versa also. Means for the inner one, if it is the anti-clockwise, then field will be something like that, downward or upward. Then in the outer, it will just reverse of that. Yes or no?
Yes, sir.
Yes. So that's a very crucial point here. So using this, we may find the just like that same concept. If rho is lying within the circle between these two, do you remember that coaxial transmission line derivation?
Yes, sir.
Yes. So likewise, using the same concept, it can be derived, and the result, if you see, the result is a bit important, not much important to provide, but bit important. That this is given, this very important result. H phi is rho naught minus A upon rho Ka. Ka is the surface charge density, surface current density inside the toroid. Inside the toroid. This is very important. Inside the toroid. Okay. So now understand the terms. What is rho naught? So you see, rho naught means if this is my entire toroid, some point, this rho naught is the distance from the center, the inner conductor, to that point where I am finding the magnetic field. Okay. What is A? A is the radius of that Amperian surface. Yes.
Yes, sir.
So this is rho naught minus A upon rho times Ka. This is the inside, and very important. What is the field outside? This is 0. So field outside a toroid is 0. Why 0? Can you try to explain why 0? Conceptually, means theoretically, forget about the derivation. Conceptually, can you imagine 0 means what could be the logic?
No, sir.
Yes. Hello?
Hello.
Yeah. I asked you something. Is it audible to you?
Yes, sir.
Yes. So I asked you something. So at least keep on responding. Otherwise, this is online teaching. It is very difficult to assume that okay, network is there or not. Yeah, means whatever is coming to your mind, at least speak it out. Otherwise, how shall I know that whether you are there or not, my voice is audible or not? Hello?
Hello. Outside the toroid.
See,
No, sir.
don't know, then no issue. At least just to try. This will means I want to you also involve in the entire process. That's why I'm asking question, nothing else. So see, I'm giving a hint. Try to apply the Ampere circuital law. Now you try. try to give the answer using Ampere circuital law.
Means outside ambient surface.
See, the Ampere circuital law says that I enclose, H
Ah,
dot dl is I enclose. If you see, current
enclosed.
in the
Ah,
inner one is the, if suppose it is like this, that is the anti-clockwise, then of course for the outer
hmm.
one it would be like this. Yes or no?
Yes.
So these two current are equal and opposite. So is there any current outside this?
No.
No. That is why I enclose is 0. If I enclose is 0, but of course H will be 0. Yes or no?
Yes, sir.
Yes. So try to apply these things.
Okay.
So this is not required really. Yeah. Now on that day I asked you and you replied that if the phi is the means phi magnetic, if this is the
Hmm.
flux, then this will be the surface integral of B dot ds. Yes or no?
Ah, yes, sir.
Okay. Now you see, can you tell me over a closed path what would be the value of this integral?
Closed part.
Over a closed path, over a closed surface, what closed
Hmm.
surface means? If I put a circle here, then what would be the value of this integral? Okay, now let me ask this question
Hmm.
in another way.
Hmm.
See, these are the magnetic lines of force.
Yes.
So suppose this is over a closed surface. Is there any
Huh.
flux? Is there any flux coming outside?
No.
No. Then over a closed path, what would be the value of this?
Okay. Zero.
0. Very, very important. The magnetic lines of force over a closed path is always 0. You can see very interesting phenomena here. This is a bar magnet. Everybody
Hmm.
has seen it, yes or no?
Yes, sir.
In this bar magnet, you see the magnetic lines of force at outside. It originates from north to south. Here it is not drawn, but inside it is from south to north. Very, very important. Inside it is south
Okay.
to north. So what does this mean? What is the physical significance of this? The physical significance of this is that on that day also I said that it is neither having source nor sink.
Okay.
Source means a starting point. It is a continuous. See,
Ah.
somebody can say that it is starting from here, going like this. I can say no. It is starting from here, going like this. So how can you say that which one is its ending point and which one is its starting point? Can you say?
No.
No. So it is having neither source or sink. Or in other
Hmm.
words, also you can say one very important statement that divergence of magnetic flux lines is equal to, what will be its divergence? Divergence is equal to
Ah. Zero.
0. Very, very important point. That divergence of the magnetic flux lines is 0.
Zero. Okay.
Why I'm saying this is important point, this will become very clear in the next slide. See, B dot ds over this is 0. Or if you apply the Gauss divergence theorem here,
Hmm. Hmm.
then what you can write? For this part, if I apply a Gauss divergence theorem, what can I write?
Del dot B equal to zero.
Yes, here del dot p is equal to 0. And this is known as Gauss law in magnetostatics. So this is the integral form of Gauss law in magnetostatics.
Okay.
See, integral form of Gauss law in magnetostatics, and this is actually the heading is here, Gauss law in magnetostatics. So this is the integral form of Gauss law in magnetostatics, and this is the differential form of Gauss law in magnetostatics.
Okay.
Yes or no?
Yes, sir.
Very, very important point. Try to make an analogy also. In electrostats, D dot ds was not equal to always 0. It was not always equal to 0. It was equal to q in upon epsilon naught, or q in. Yes or no?
Yes, sir.
But b dot ds over a closed surface is always 0. There del dot d was rho v, but del dot b is 0. Getting my point?
Yes, sir.
Very important, these things. Very, very important. Then there, for the static electric field, I told you that this is conservative in nature, means its curl is 0. So del cross E is 0.
Yes. Yes.
But here I have taught you that del cross H is equal to J.
Ah.
So its curl is not 0, but that curl is 0.
Yes, sir.
Sorry, this is equal to J, not 0. Del cross H is J. So this is the Ampere circuit law. So see,
Yes.
here curl is 0, but here curl is never 0. Their divergence is not always 0. Here divergence is always 0. And zero divergence means it is continuous, neither source nor sink. That divergence
Okay.
cannot be 0 because that starts from positive and terminates at
Negative.
negative. Exactly. Right?
Yes, sir.
Understood?
Yes, sir.
Now we will see the last thing for today. We have studied these equations and they are all together called as Maxwell's equation. That's very, very popular. I hope you must have heard at least in your while you were studying in
Yes, sir.
So what Maxwell's equation are nothing. These are the 4 laws assembled together. That is the Maxwell equation.
Okay.
So see, here one important point you should note down. Maxwell equation for a static field. Why I am stressing this point, static field? Because the next module, in the next class, I will start with the time varying field. Till now, both the fields are static with respect to time. They are not varying with respect to time.
Time.
To see, del dot D is equal to rho v. We have studied, yes or no?
Yes, sir.
This is Gauss law in electrostats.
Ah.
Del cross E is 0 for a static field. It is always conservative, yes or no?
Yes, sir.
Del cross H is J, we have studied.
Yes.
And del dot B is 0. So this is the differential form of Maxwell's equation for a static field. Remember. And once we will study the time varying field, this equation, you see this equation and this equation will get changed. These two will be the same. But for the time varying field, there will be a change here. This will not equal to 0 for time varying field. This will not equal to 0. For the time varying field, this will not equal to 0. And here there will be one more term that will be del D upon del T. This will be added. That I will explain, but just I'm telling you that what is the difference between the Maxwell's equation of a static field and Maxwell's equation of time varying field. Are you getting my point?
Yes, sir.
Yeah. So these two equations will get changed. Yes or no? And if I ask you that from here, state me the integral form of the Maxwell's equation, can you?
Integral form.
Of Maxwell's equation. So of course we can. Yes or no?
Yes.
So what will be the first integral form?
Dot product.
Very simple, right? It
Line
is the sum
integral.
of Gauss law.
Yes, sir. Line integral.
No, not line integral. For here.
Here
Here it will not be line integral. For curl, it is line integral.
means
For divergence, it
line
will be
integral.
surface
Okay.
integral.
Surface integral.
Huh?
D
Surface
dot
integral.
ds
Yeah, d dot ds is equal
equal
to open volume integral rho v dv.
to volume integral rho v dv.
Yes.
Ah,
Here it is line integral e dot dl is equal to 0.
here line integral e dot dl equal to
Here line integral h dot dl is equal to surface integral j dot ds.
line integral h dot dl equal to j.
No, surface
J
integral
dot
j dot ds.
j dot ds. Yeah, surface integral j dot ds.
And here it is again
Here
surface integral v
surface
dot ds open
integral
close path 0.
surface integral v dot ds equal to 0.
Yes, very easy. Here all those have been written. See. Yes or no? Maxwell
Yes,
equation
sir.
in integral form. For static field, again I am stressing the word static field. For dynamic field, dynamic not time varying field, this will get change, this will get change.
Okay.
Okay?
Okay.
So today we will stop here. Tomorrow I won't be able to take the class. Day after tomorrow, again I will take a class. So 5:30 you are
Okay,
not
sir.
free?
Day after tomorrow, I will be free, sir. Today I had a lot of work.
Okay, no issues. And on 25th, you must be having a holiday at your office.
Yeah. Yes, sir.
So, okay, so then we will go for the 2 consecutive days and we will try to finish up till the EM wave propagation. Okay.
Okay, sir. Okay.
So go through the things
Okay, sir.
till tomorrow. Day after tomorrow, again, maybe 5:30 or 6 accordingly. I will also see my commitments. Again, we will
Okay,
sit
sir.
for just like here. And 25th, better we would be going in the afternoon or morning likewise because you will be also having the holiday. Okay.
Yes, sir.
Okay.
Yes, sir.
Yeah. So I will inform you and you see your commitments and then we will, as usual, we will synchronize and then we will.
Okay, sir.
Okay.
Okay, sir.
Okay, fine.